today's lecture is chapter 5, problematic soil. Just a reminder of what we have taken before. Chapter 4 was isolated footings. Chapter 3 was bearing capacity and settlement. Chapter 2, shallow foundations. And chapter 1 was types of foundations. So now we reached chapter 5, problematic soil. Actually, all soils are problematic. But when we say problematic soil, it means that problems that is very difficult to be solved. Because as you know, soil is not a normal material. Soil is different from concrete, soil is different from steel. Soil is a combination of different percentages of different types of soil. So each time the percentage will differ, the constituents will differ, the amount of voids will differ. So soil in general has lots of problems, but we know how to deal with it. It is easy to deal with it, or we have already learned how to deal with it. But recently we started to face new types of soil that are problematic, really problematic. It means that it is better for us to remove it and bring another type of soil. Another type of soil that we know the problem and we can solve it easy. But these problematic soils are very problematic to the extent that I prefer not to deal with it, or it will be very difficult for me to improve the type, this soil to be used. So this is the definition in geotechnical terms, is a type of soil that causes additional engineering problems due to its composition or changes in the surroundings or changes in the environmental condition. So this type of soil is really problematic. There are many types of this soil, but the most widespread in Egypt are 3 types. Expansive, collapsible, soft clay. Expansive mean that the volume increases a lot. When I speak about clay, any type of clay, when I add water, the volume increases. But increases to a certain level that I can deal with it. But in some cases, in rare cases, the extent of the increase is enormous. I cannot deal with it. I cannot use it as it is. I have to change, either to replace it or to change the characteristics of this soil. So this is the first type, which is the expansive soil. The other is called collapsible soil. Collapsible soil means that it has the tendency to collapse. What does it mean? It collapses. When water comes to this type of soil, it changes the characteristics of the soil, and the structure of the soil collapses, and we find that it will settle a lot. The third type is called soft clay. Clay in general, when it is subjected to water, is soft or softer than the normal. But in some cases, it is extremely soft. Extreme to the extent that it cannot carry anything. It may not carry yourself if you are walking on top of it. So this time, if it cannot carry a human being, then it will not carry any structure. So it is a big problem. These are the main 3 problematic soils in Egypt. but there are lots of other problematic soils outside Egypt. But these are the normal cases in Egypt that we have to study. Expansive soils, you can check this as just an example, but normal expansive soil are much more than that. This is the pavement, and you can see that there is a bulge here and here. What is the cause of this? Because there is a layer of expansive soil beneath this. It's a problem for this pavement, but when this happens on a large scale below a building, it's a real problem, because the whole building, you may find that the soil is carrying the building maybe 10 to 20 centimeters above ground. It's a lot. Collapsible soil. From this photo you can see it's a new building, and obviously they haven't reached they are still in the construction stage, because the streets outside are not paved, and even it's not ready for anything. But before anything happens, you find that here lots of cracks. Why is these cracks happened? These cracks happened because the soil beneath this ground is collapsible. So once they finished the building and they connected the pipes, the water pipes and the drainage pipes, maybe there started to be some leakage at any location. This leakage meant that water reached these layers of collapsible soil, and this collapsible soil collapsed, causing these cracks in a newly built building. Soft clay, it's the photo speaks. This is what you expect in a soft clay soil. It cannot carry anything on top of it. There is another type that was added to this lecture. It's called sinkholes. Sinkholes really it's not a soil. A sinkhole is a hole in rock, but it is problematic. We can say that it is a problematic rock. It's not found a lot in Egypt, but it is found. This photo is taken in Egypt, below a road in the north coast. So it is found in Egypt. It's found in everywhere. So we have to know it, because we may face it in the future. They say here that it is problematic soil is everywhere. It causes complications to the structures. Therefore, engineers must answer several questions for each one of these types. What is the probability? These are the questions that we should know about this soil. What is the probability of the presence of these types? Because as we said, if this type is not present in Egypt, then we don't have to concentrate on it at the time being. You know it in case you meet it in any place outside Egypt. Why does this type of soil pose a problem to the structure? What's the problem does it cause? How can we, I'll just go through it very quickly. How can we discover this problem during our site investigation? How can we classify this type of problem? How can we treat this problem? Or how can we change the type of foundation to be suitable for this type of soil? Starting with the first one, which is the expansive soil. It is found a lot in Egypt. It is found in Nasr City, Abur City, Shuru City, 6th of October City, 10th of Ramadan City, Fayoum, Sadat. As you can see, these are all, with the exception of Fayoum, they are all new locations. These are not the old locations that were used in Egypt decades ago or hundreds of years ago. This was newly new places that were used recently. It means that this is a problem that started to appear in Egypt lately. Before that, we were living in say 100 years ago, more than 100 years ago, all of Egypt was located either around the Nile Valley or in some places in the desert or at the coast. So these are the three common places for living in Egypt. But lately, they started to have new cities. These new cities are big cities at new locations around Cairo. Nasr City, Obol City, Shuruk City, all of these are new locations. Why this happened, we will discuss this after studying also the collapsible soil. Problems and influencing factor. Why does this type of soil cause damage to the structure? The soil is affected by moisture, causing a change in its volume. Actually, it's not by moisture, it is by wetting, because it's not just moisture that causes the problem. If water in big quantities reach this type of soil, it affects the soil, and we have our two main types of foundation: shallow foundations and deep foundations. Some soils will be good for shallow foundations, some others will be good for deep foundation, some will be good if we remove it and bring another type to replace it, and so on. The second type, we said that the first was, this was the first, the expansive soil. So the expansive soil, we are still in the expansive soil. Attention should be paid to creating a suitable program of site investigation to study this type of soil. Why we should pay a lot of attention? Because actually in site investigation we use water. And we said that this type of soil is affected by water. So if I use water in site investigation, it means that I will maybe eliminate the problem during site investigation, and I will take sample that has already been affected by water. I will take these samples to the lab. The lab will not discover any problem and will tell me the soil is very good. So I need to define a very good site investigation problem to take a sample in its intact condition and take it to the lab to discuss it, to study it, or the opposite, to study it on site, to make some investigations on site. This is a shot from the Egyptian Code of Soil Mechanics, and this is its translation. There are many types for site investigations, but the best for this type of soil is to use open pits. Why open pits? Because in open pits we do not use water. We just drill and we go by ourselves and take samples from the soil itself. So in this case I will take samples that are in good condition. But actually the problem is that open pits are very shallow. I can only investigate 2 to 3 meters using open pits. But suppose I have problematic soil at 5 meters, 10 meters, then I will not be able to discover it by this method. And I will have to use boreholes, but in this case it is better that I would use boreholes that does not use water in the drilling operation. Is there an equipment that uses? Yes. Because water is mainly used in the drilling machine for cooling the machine during drilling. I can use some types of machine that use air for cooling, like you remember in cars, you have water that is used to cool the engine, but there is a type of car which is the Volkswagen. The cooling system does not involve water, it just involves air. If you remember the Beetles, the small car, the Volkswagen, one of the advantages of this type was that it uses air, not water. You don't use. So there are machines that use air for cooling, not water. So this will be very appropriate for site investigation. This is a photo for an open pit. This photo was taken in site investigation in Yemen, in Sana'a airport. There they have the ability, I think we discussed this maybe in a previous lecture, they can go with open pits maybe to 8, 10, 15 meters. In this photo, this is the helmet of a person standing below, so it is at least 8 meters and they can go more than that. But this only happens at this location. Usually in any place, open pits do not exceed 2 or 3 meters as a maximum. This is the boreholes. This is the normal machine for mechanical drilling. We can drill holes using this machine. And if you see next to this machine, there is some kind of arrangement that is used for the cooling water. Here the water is in a pit here, and it is circulated to cool the machine while drilling. Of course, if we use this type in a site investigation, we have to use it without water to be able to get good samples. Once we do our site investigation, then we can take samples, we can perform some experiments in the lab. These experiments deal with the plasticity index, shrinkage limit, liquid limit, and so on. These are all Atterberg limits. So based on these Atterberg limits, I may be able to classify the degree of expansiveness of this soil. So there are ways in site investigation that we can classify, and we can say that this is very high expansive, this is very low expansive, and so on. This is the translation of the table. There is something called soil improvement. Soil improvement, this is also from the code, and this is the translation. Soil improvement means that I find problematic soil, I cannot deal with it in this shape, I have to change it. Either to change it by replacing it, taking it away and bringing another good type to replace it, or treating it in place. So either replacing it or adding something, or trying to prevent water from reaching to it, or whatever what we can do to improve the type. Of course, if we are going to study soil improvement, there should be a chapter for soil improvement alone, because there are many ways to do soil improvement, either by adding something, by changing the characteristic of the soil by some kind of compaction, some kind of anything that would change the properties of this type of soil. But it needs a special lecture. For the meantime, you have to understand that in some cases we do soil improvement, and the best way for soil improvement is to replace the soil. If I cannot replace the soil, then I have to do something for the existing soil, but there are many ways that we have to study. So here, as we said, that in some cases where we are going to use replacement, it does not mean that we are going to replace the full depth of the problematic soil, the expensive soil. Maybe I would remove 2 or 3 meters. This is the range that I can easily reach, and this is adequate in case whatever below expands, the above layer will consume this expansion, will help in relieving the pressure of this, so that it would not reach the foundation on the top. Soil improvement, we have lots of way. One of them is to, as we said, replacement. The other is to try to prevent water, though I do not believe in that. Whatever you will do to try to prevent water from reaching, it may work for a while, but later in the future water will reach and it will be a problem. So I can use it only as an additional factor of safety, but not the main safety factor. The other is to use, say, piles, change the foundation type. If I change the foundation type, maybe I would use a better type of foundation. Piles are not good for expansive soil, because once the soil expands, it may crack the piles itself, because the expansion is very high, and it may induce horizontal forces on the pile and it would crack it. So the best thing for this type of soil is to use either shallow foundation or raft foundations with openings to relieve the pressure of the expansion. And so on. There are many ways. I may use additives. I may add some chemical materials to the soil to relieve this pressure. There are many ways, but for the time being, as I said, if we want to study soil treatment, it needs a special lecture for soil treatment. Maybe if we have time at the end of this term, we can have a lecture for soil treatment as a whole. But for the meantime, you can just understand the meanings of the methods that are given here for soil treatment, just names for future study. Soil replacement, as we said, is the best and the most economic way for treatment. If it is possible, then it will be very good. But we have to stress on the fact that when I bring the new soil, I don't want to remove a problem and bring another problem. If I remove the expensive soil and bring good soil and just dump it in place, then this dumped soil with time will settle and will induce lots of problems to the structure. So I have to put very well compacted soil. I should put this new soil in layers. Each layer would not exceed 30 centimeter, compact each layer, and so on till I reach to that I have replaced the full height required to be replaced. Types of foundation. The best type of foundation is the isolated footings. We said why? Because it helps in relieving the stress. But in this case, if I use isolated footings, I have to be sure that all the footings will work together, because expensive soil does not mean that it will expand in all places with the same extent. Maybe it would expand a lot below one column and expand a little bit below the other. So I have to connect these columns with very rigid tie beams or ground beams, so that in case of differential settlement they would work to help not to affect the superstructure. Raft foundations, we said that raft foundation is the worst type of foundations for this. So this is an example for how to pay more and get less, because you are going to use a very complicated and expensive type of foundation to get the worst behavior of soil, because it will be on top of the expensive soil. The expensive soil will carry it up, and the structure will be, at least in the good condition, it will be lifted as one body. But in most cases it would tilt, it would crack, lots of problems. So if I want to use raft foundation for special reason, then I should use raft foundation with openings, so that I help in relieving this stress. To know how is the behavior, or this is just to know what is the behavior of raft. Suppose you have a raft and you have expensive soil in the middle, or you have a raft and you have expensive soil in the two sides. But here we are speaking about putting a raft on a soil with limited amount of expensive soil. So in this case, the raft can carry whatever, because they are just minor changes, not very big changes. So, but in this case, these are the expecting straining actions on the raft. This is the bending moment, the shear, the deflection, and the soil pressure. This is how the raft will behave in case I have expensive soil locally at one location below the raft, and the raft is very big and heavy and it can carry, but I will have to add, say here, I will have to put extra reinforcement at the top layer of the raft. In the opposite, if the opposite will happen, then I need to put extra reinforcement at the bottom of the raft, and maybe a negative at the sides, all around the sides of the raft, and so on. This is just for you to understand in case you are faced with having raft on expensive soil. But of course, to have this case without problems, it means that the expensive soil are not that strong. It's not very strong expensive soil. It's just minor expensive soil, so the raft can manage with some additional reinforcement. But this does not mean that I can use raft for managing expensive soil. No, it is better not to use it at all. But if you have it, then the check you should do is to add additional reinforcement so that it would help in overcoming these local spots of expensive soil. Deep foundations. Deep foundations piles, we said also that they are not good. Why? Because once the expensive soil starts to expand, it expands to the top, it expands to the right, to the left, everywhere. So if I have piles, then the expensive soil will exert horizontal forces on the piles, and it may crack the piles or induce additional horizontal forces on the pile. So they say, if you, in the code, but I'm not in favor of that, if you want to use this type of piles, then they say that use piles with enlarged ends. What are piles with enlarged ends? It's the same original pile, but the bottom of the pile, instead of being with the same cross section, in construction they make it bigger, so that if the footing wants to, if the soil wants to carry the footing up, the enlarged base of the pile prevent it from going up. It is very difficult in construction. You cannot depend on it. There are many precautions for this. I do not prefer it. It is very expensive. So I'm just we are just saying it because it is given in codes, but it is better not to use deep foundations. And if I use deep foundation, then I should not depend on it on resisting the expansion. I should do my best so that maybe the piles would have double casing around it, so that if the pile wants to move up, it can move freely without affecting the soil around it. It's a problem, so it is better not to deal with it. I've used this type of piles before, but it was a problem, and the gain or the benefit of using it was not that good. The best thing is to replace it with isolated footings, with very rigid. Pay whatever you want to pay in increasing the rigidity of the tie beams, or use raft with very big openings. It will be much better than this. This is what we have said before, and so on. These are the piles with the enlarged base that I was speaking about. This is the normal pile. They come to the last end of the pile, and they use a special machine that enlarges the void below, so that when you pour the concrete will fill all this space. If the soil wants to expand, it will move up. The pile cap will be on top. It will push the pile cap to the top. Once it pushes the pile cap to the top, the pile will prevent the pile cap from moving because it has an enlarged base below. It's very difficult, and to have this, I have to put reinforcement. How can I put I may put concrete, but how to put reinforcement below? In this case, it will be just plain concrete. So I don't believe in that, by the way. So it is better not to use it at all. This is my opinion. Of course, there is another type of deep foundation, which the caissons are very big, very strong. If I tend to use these caissons, then I, as I said before, use double layer or put some kind of insulation material, so that if these caissons, if the pile, if the swelling soil wants to swell and go to the top, then the pile will not be affected, because the pile can move freely without being affected by the soil. It's not also good, very complicated. I believe it is for research better than using it in practical cases. This ends the first part of the collapse of the problematic soil, which is the which is the expansive soil. The other type is the collapsible soil. We'll go here a little bit quickly, because it will be similar to the first one. The only difference, we are going just to concentrate on the differences between these two types. Where it is found, north coast, 6th of October, Obur City, Burj Al Arab, El Hammam City. Also, most of them are very recent locations. These are new locations. It means that problematic soil are only found, are mainly found in new regions. Why? Here I said that we are going to discuss this when we reach this point. Why do we have this? It is because of the method of formation of this. How this problematic soil was formed. This problematic soil was formed mainly during the floods. If you remember recently, when we have in Libya the flood that happened in Darna, you've seen lots of photos. Water coming with enormous amounts, carrying everything with it. And of course, it is carrying cars and buildings, so it will be carrying soil from everywhere. And taking this soil and moving with it, going to the low areas in the desert. This is what was happening in Egypt long time ago, before the high dam. Before the high dam, we used to have floods. So what happens during the floods? Water increases, comes very quickly, takes sand, gravel, clay, mud, everything, and crushing them all together and taking them away from one place to the other. So what happens is that once it reaches around Cairo, it starts going to the right, mainly to the right because of the topography. So it goes to the area where we now have Obur City, Shuru City. These are low areas that were affected by the flood very long time ago, before the high dam. So it carries these new types of soil affected by water and go there. And it will go as much as the flood can push it. Then it will reach a location where the flood is finished. So water has to reside. So it will settle in place. Everything that was going with the water will settle down in place with water. Then water will start to seep and will leave this crushed formation in place. Then the flood will be finished. Maybe we don't have flood in the next year or in the coming 5 years. Nobody knows. During this period, other sand dunes and transported soil from other location will come on top of this. And so on. This happens every now and then. When we had the high dam, floods stopped. So in these areas, we find that we have layers below the ground, maybe 5 or 10 meters below the ground, and these layers were previously affected by water coming from the flood, and they stayed in place and were not affected by water since then. What will happen? What will happen is that when you put your building on top of this layer, and then you connect water to this area, and water starts to leak, water will reach these layers that are very, very aggressive, and they need water to release the bond was there between the particles, between different soil particles. So once water come again, they will start to be affected by water. This is a quick explanation why this started to happen in these new areas. So now you expect to see problems in any new area. You have to check, is there this type of soil or not? It will not be layers, it will be just what we call it, it will be something like, in Arabic, like a strip. You will find a strip below an area. In this location was a low area. So when flood came, it just followed this path of this low area. So that's why it is found in Egypt. Now you know why it is there and why it is affected by water. We discussed this and we said that it is not humidity, it is wetting. When water come and fills the area, it causes problems again. We said that in site investigation we have to follow a good procedure for site investigation, because if we use water in drilling, then we are going to change the characteristics of the soil. This soil is affected by water. If you affected by water during site investigation, then the sample will be already affected by water, and once it reaches the lab, they will not know that there was some kind of cementation in this material. They will not know, because you have already sent a sample after losing the cementation of this soil. We said that it is better to take samples that has the normal water content of this soil. So the methods that we can use for site investigation is either open pits, where we don't use water, or mechanical drilling but using air cooling instead of liquid cooling system, or to do testing for the soil in place and do it maybe twice. One before adding water and one after adding water. So by conducting the test twice, one with water and one without water, we can assess what happens to the soil due to the effect of water. As an example of this is standard penetration test. Standard penetration test is the test conducted on site. So using this test we can we can investigate what is happening to soil due to wetting. This is the SPT test. I think we discussed this SPT test before. As we discussed before, this is the shape of the equipment, and I push this equipment 15 centimeter and another 15 and another 15, and I count the number of blows and take the number of blows of the second and third portion, add them together to get the end values. If I get the end value before adding water and the end value after adding water, and I found a reduction in the number of blows, it means that this type of soil is affected by water. Another type is the plate loading test. You remember the plate loading test? It's a plate where we put a hydraulic jack on top of it, and there is a reaction on top of this hydraulic jack. Once I exert pressure on this hydraulic jack, the pressure is exerted on the soil, and I check the settlement of this plate. I can do this according to the Egyptian code. It states exactly what we can do for this type of soil. We can reach, say, to a stress of 2 kilograms per centimeter square. Once I reach this level, I start wetting the soil and then continue the test. If I notice that there is a big change in the soil behavior due to wetting, then this type of soil is affected by, it is a problematic soil and it is affected by water. This is how the test is going. Here is the stress that we are applying on the load. Here is the settlement. So as a beginning, once I put my plate, I will find that under own weight, the plate will settle. So this is before adding any load, I may have a few millimeters or parts of millimeters due to the own weight of the plate. Then I start adding this jack would work, so it starts to exert pressure. Once I exert pressure, I have settlements, and so on, settlement till I reach this point. When I reach this point, I start adding water without adding more pressure, just the same pressure, but just adding water. I will find that there may be a sudden drop in the settlement. The settlement will increase, though I am not adding water, I'm not adding load. It means that due to water itself, there is settlement, not due to the pressure, because I was reaching, say this pressure is 100 kilonewton per meter square. At this location, I don't have any additional settlement. But if I add water and I have settlement, it means that the water affects the characteristics of the soil, and under this pressure I will have a drop. The more I have in this drop, the more the problem of this soil. If I don't have any change, it means that, suppose you have normal sand, very clean sand, and you reach this level and you add water. Water will come in the voids and will percolate. Nothing will happen in the soil. You will find that this length is zero. Nothing will change. So it means that this soil is not problematic. But if I have a very big drop, it means that I have a problematic soil, and there is a measure for this drop, how many, and according to this, we can measure the degree of collapsibility of this soil. Then, once the settlement stops, I start to add additional stresses, add more load. You will find that when you add more load, you will have additional settlement. But if you look at this slope and you look at this slope, you will find that they are different. Why they are different? Because here it was in the dry condition, and here it is in the wet condition, because I already have water now. So it means that this soil was affected twice. Affected at the beginning to have this sudden drop, and then affected later in its behavior because the characteristic of the soil changed, and the reaction to the load will differ than before. If before it can carry a lot of load to have a settlement of 1 centimeter, in this case it will maybe take less load to have this settlement of 1 centimeter. So this is the main difference. From this chart we can analyze the soil very good and know exactly how problematic is this type of soil. Now we can go to the next part of the lecture. Of course, we are still within the collapsible soil, but we are going to discuss the soil improvement, we can stop for this part and continue the next part.